Well, good evening. I'm Charles Schultz, and this is the Randomizer for March 1st, 2022. And we have an interesting subject tonight. The subject matter is C.F. Powell. C.F. Powell, or Cecil Frank Powell, was a physicist, and he was a Nobel Prize winner in 1950. We're going to get into his achievements and some of the interesting things about scientists in general. He kind of inspired a couple of thoughts in me that I want to share. Before we get rolling, I want to invite everybody to go to the Schultz Laboratories website or the Universe Science Center website. Sign up, become a member, and support our efforts. We're growing more material, adding more galleries, and if you have a specialty you like to teach, we could even set you up with a gallery or classroom online in a virtual space of your own so that you can hold your classes there and your students there. Now, I'm broadcasting today from our physics room and structure of matter particularly, and I think it's particularly relevant because C.F. Powell was a physicist and he dealt with particle physics. So this is going to be an interesting discussion. Born in 1903 in England, he was a real scientist. I mean, he eventually worked with the Cavendish labs, and you may remember Cavendish was the fellow who figured out gravitational strength in Cambridge. And one of his bosses was C.T.R. Wilson. If any of you are fans of physics, you know what the Wilson cloud chamber is. It's a small device. You place a sample of radioisotope by it, and you can literally see the particles trails in the fog in the chamber being made as they fly. So it's a simple diagnostic device for spotting nuclear trails. It's a very simple indicator. So he worked in the Cavendish lab with Wilson, and he studied condensation phenomenon. Among other things. Why condensation? Because the cloud chamber uses condensed vapor to reveal the trails, so it's a natural connection. Now, it's interesting. He had a broad field of interest, and he was into many different things. In 1936, he traveled to the West Indies to study volcanic phenomenon, and as a result of the work that he did there, actually, the country of Grenada issued a stamp with his picture on it. I thought that was kind of an interesting perk, I suppose, for being a good scientist. In 1948, he was actually promoted to professor of physics, and he began a study of positive ions. And in order to do this, let's look at what an ion is. A positive ion is an atom that's had a few electrons removed so that it's positively charged. And so he needed to make positive ions to do the study. So he built what was known as a Cockcroft generator, a very powerful high voltage generator, and he used it to create his own ions. And he would accelerate them and look at how they scattered the nuclei of other atoms. So notice, this is a fellow who took the drawing of the generator, built the high voltage machine, made his ions, and smashed them into other atoms and saw how they scattered. He was a hands-on researcher, as you can tell, going to study volcanoes on site, working with the inventor of the cloud chamber, and building his own high voltage machine. What's more interesting is he started developing special photographic emulsion. Now, a lot of people don't know what an emulsion is these days. In times past, you often had to make your own photographic plates, which were usually made by coating a chemical of some certain composition onto a plate of glass. And in this case, the emulsion was obviously a mixture of something that could sense light, which normally meant a silver nitrate compound. There are others that'll do it, but silver nitrate is easy to get, easy to make. So he formulated a new emulsion and made his own plates and used them to study radiation and particle tracks, very much like what happens in the cloud chamber that I mentioned. What he would do is he would place them on mountaintops where the air is much thinner and particles from space, such as cosmic rays, can come in and strike the plates, or he would send them up in specially made high-altitude balloons. So he was involved in making and delivering these plates to the locations where they were most likely to get cosmic particles, cosmic rays. Now, a cosmic rays could be any element, but they tended to be elements that are in space that have been ionized by radiation and then spun up to speed by the magnetic fields of stars or intense fields around certain planets, mostly around things such as magnetar stars or pulsars. And cosmic rays come in all directions from the sky as a constant rain of energetic particles. They carry enough energy that when they strike the atmosphere, they explode, and the fragments are charged. Now, you may have looked at the stroke of lightning and wondered how the branches and forks in the lightning form. This is the path of the debris of a cosmic ray strike. So a particle from space comes in nearly at the speed of light, strikes an atom on the way in, fragments into all these paths, and then those fragments are energized enough to fragment some more atoms, and you end up with this branching, forking set of paths from a single atom, ionized to near light speed. What this does is it creates charged pathways in the atmosphere. And the charge of lightning follows those pathways. I wrote an article about this back in 1992 called Cosmic Rays, Lightning, and Life. And in the article, I pointed out that the lightning paths formed burn a lot of nitrogen with oxygen and make nitric oxide, which goes into the solution in the rain and creates weak nitric acid, which then goes on to fertilize most of the plant life on Earth. If not for this process, probably 90% of the plant life on Earth would not exist. This is a natural means of promoting plant growth through addition of nitrates created in the sky. So there literally is a link between cosmic rays, lightning paths, and the formation of life on Earth and the sustenance of that life, the plant growth. So his work made the emulsion that captured these paths. Now, what's interesting about this is the most amazing thing. His photographic plates captured particles they could not identify. He was able to find these tracks of nuclear particle collisions, and he discovered in 1947 a particle called the pi meson. Now, what's significant about this is there was a Japanese physicist in 1935 that predicted this particular particle should exist, and his name was Yukawa Hideki. So the particle had been predicted, but nobody had seen a sign of it. 12 years later, through his invented his emulsion that he made and his film plates, he was able to actually capture and prove the particle existed. So in 1949, he received the Hughes Medal for his work in physics. And in 1950, he was granted the Nobel Prize for his development of the photographic method of studying nuclear processes and his discoveries regarding mesons made with this method. Now, a meson is a middleweight particle. Protons are heavy, they're baryons. Electrons are very lightweight, they're leptons. And baryos and mesos and leptos are Greek words for heavy, medium, and light. So now you know where the names of those particles come from. It relates to their mass. And the pi meson is about 200 times as massive as an electron, approximately. So middleweight nuclear particles. They're also unstable. So what's interesting, several years after the discoveries, he made the discovery of pions and muons, and the further decay of those muons into electrons using the same technique. Now the deal is, a muon acts like an electron when it's negatively charged, and in some cases it can actually replace an electron and orbit an atom. Interesting things come from that, and that goes into the work of Andrei Sakharov, the nuclear physicist, and some other things, which I won't talk on tonight. But what's interesting about a meson is this. It has a limited lifespan. It is not a stable particle. And as a result, after a few milliseconds or so, it breaks down, and one of the things it emits often is an electron. So his emulsion was able to track the wreckage of these decays on film and show without a question that this is what was happening. So one thing that stands out here, and this is very important, he worked with many other physicists in the course of his career. And many of them made suggestions and pointed out that, looking at the time that these paths last, and if a magnet was there, it would curve the path of the particle. Looking at the amount of curvature in the path, you could distinguish between a proton and a meson very easily. So what stands out is this. He gave attribution to the other physicists for his discovery, and he said that it would not have been possible if they had not pointed these things out. So I see a number of things here that most people don't think about when you think of a physicist. You think of a little guy with a bow tie and a clipboard in a laboratory. Well, guys, I don't think that I believe the theories. No. Let me throw that complete image in the trash. Physicists tend to be passionate about their work. They tend to be involved in it. And they get out there with a shovel or a blowtorch or a magnetron or whatever, and they build what they need to do the job. They are the ones who have a visceral experience of whether they're right or wrong, of how the hardware has to operate, how to build it, and how to make it give you results. But not only this, a truly mature researcher, any human being for that matter, has the grace to admit that they didn't do it all themselves, that their work stands on the works of others, that they will give credit to other people who they've worked with and say, so and so here made a suggestion, and that's what made this possible. We tend to take full credit for things that we do, and this is not true. We don't do anything in a vacuum. And one of the signs of maturity is to have the ethics and the heart to extend credit to those who have helped us or have given us the ideas, shown us the proper path. So what's most amazing here is this is a real man. He took credit for the work he did, but also gave credit to those who supported it. He learned how to build the hardware. He learned from first principles. If you go back to scientists in the 16, 17, 1800s, and you look at their work, you discover they didn't have anything to work with. They started with less than you have in your home. And they would refine the material, they'd hammer it into shape, they'd drill the holes, they'd consult with people, they would build their equipment. The most important takeaway from this is, if you want to do something of significance, get your hands dirty. I can't tell you how many times I've had to blow something out of glass, or machine something out of a block of brass or aluminum, or weld something together, design and program the circuitry, and it's the only way you ever know for certain what you're doing. When we look at the people who claim we never went to the moon, you look at scientists in NASA today and you say, these guys have a picture. You go to the computer and you put in some numbers and you get, here's how we're going to do it. No. I call this the catastrophe of the slide rule. I actually named it up. Made a name for it. And it's important to understand this. In times past, before you had computers to do the work for you, all of your calculation was done with a slide rule. You had to understand just exactly how to operate this mechanical device to get your numbers. You had to understand internally how to approximate. When you had an answer, you had to look at it and go, that doesn't look right. That just doesn't look right to me. Engineers in the past had a gut feeling for when the solution was pretty close and when it was wildly off base. We have the catastrophe of the slide rule today, in that most people haven't a clue. They just think magical, this will work, that will, therefore, this is... No. You have to understand your materials, the medium, the methods. You've got to understand how things work. And C.F. Powell was a true scientist who understood these things. And I think that's one of the things that leads you to success. And so I get a little passionate about this because a lot of people who have never worked in a field just pop out an answer, well, it's got to be this. And they don't understand a lot of the underlying principles and a lot of the legwork that it takes to succeed. When you succeed as a scientist, that credit doesn't just shine on your work, it shines on the work of those who came before you. And at this point, there is something that comes to mind, and I always quote a verse every day on one of these randomizers, and I think it's necessary because it's the bounding of ethics. And this particular quote is from Galatians 5:17. For the flesh lusts against the spirit, and the spirit against the flesh. And these are contrary to one another, so that you do not do the things that you wish. Your personal desires or preferences will wreck you. You have to be impersonal enough and in control of your soul enough to set things aside that misdirect you or consume your time, your resources, and time literally is the only resource you have. Think about what you're doing. Think about what you want to achieve and how you're going to reach that focus. What do you need to throw away out of your behavior to allow you the laser sharp focus to get the job done, to achieve what you wish? And I'd say that's pretty much everything I need to say tonight. So if there are any questions, the floor is open. And I'm going to go on to say, I encourage everyone to come to the Universe Science Center and Schultz Laboratories. Sign up, get your Oculus, walk through the galleries, experience it, and share it with your friends. Support what we're doing and help us to grow. And at that, I imagine that this is the end of the randomizer for today. And join us tomorrow at 6 p.m. Eastern Standard Time for another randomizer. Come in, join us, give us your questions, suggestions, and ideas, and we'll be happy to answer them. With that, have a wonderful evening, and please do make the world a better place. And thank you very much.